Okay, so we continue from where we left off. We have obtained this expression, and we now want to proceed to a state where we can say that, oh, so this was what the shear strain was all about. Okay, so it may not be obvious from here, but we'll start dropping terms, okay, making mathematical approximations. So on the left hand side, you see, if you multiply all of them out, surely you are going to get this quadratic combination, epsilon 1 into epsilon 2. And on top of that, cos theta is also there. Now cos theta may not be small. Okay, cos theta dash may not be small, but surely epsilon 1 into epsilon 2 is small. Now this is where I am going to leave you feeling a little bit unhappy. Unhappiness is that even the terms which are epsilon 1 into cos theta dash will drop that also. Okay. The thing is that cos theta dash, no matter what, it is not greater than 1. Okay, it is not greater than 1. Now, epsilon 1 is very small, is really very small. Meaning that in the kinds of engineering problems that you are going to do, you will see in your tutorial sheet, the usual values are something like 10 to the power minus 4. Okay, so if you have 10 to the power minus 4 multiplied with something like 0.6, it is still quite small. Okay, so it is with that kind of a hand waving argument that we are going to drop it. Okay, so what remains on the left hand side is just this. So you are going to get a cos theta dash. On the right hand side, that n1 dotted with n2, capital N1 dotted with n2, what is that? That is just cos theta. Plus now do you recognize how the shear strain will come? How? No, nothing like that. Not so much manipulation. So see, let me remind you. So as it stands, our answer has been found. Okay, whatever that objective was, that given theta, you find out theta dash. I have erased that part. So given theta, you find out theta dash. That much has been obtained. Okay, so theta, if it is given to us and the state of strain at a particular point is given to us, we know the unit vectors along the line segments that we are interested in, then we can find out the change in the angle between them in the deformed configuration. So that answer is found out. But all of these things were towards this, directed towards the motivation of finding out an expression of the shear strain. So what we'll do here is that we'll go back to the fundamental definition of shear strain, which started with the story that we have two line segments which are perpendicular to each other. Okay, so if this happens to be the xy plane, then these two line segments initially are along the x and y, and we'll say that the change in the angle between these two line segments, which are respectively oriented along the x and y, will give in the deformed configuration something like this. So this change angle, these two things, this is the gamma. Okay, this change in the angle. Okay, so whatever this change in the angle and whatever this change in the angle, if you add them up, that is the gamma. Okay, now initial angle is theta is equal to 90 degree. So as a special case of whatever we had discussed in the previous topic generally, can we now consider that this is PQ and this is PR, which means that theta is equal to 90 degrees. Now if theta is equal to 90 degrees, it quickly opens up a nice gate there. Okay, so this theta dash, what is the theta dash? This is the theta dash. Okay, and what is the theta dash? This is cos of pi by 2 minus gamma. Very good. And on the right hand side we have a 0. What is this 0? This is the cos theta 0. Okay, cos theta is 90 degree, that is why it is 0. Plus whatever we have here. Nothing to change there. And now you know what I'm going to do. This is going to be sine gamma. And if gamma is small, okay, this is the expression of the shear strain. Now just take a moment to, behold its beauty. So what is it telling us? So at a certain location, at a certain point, you have the state of strain, this. Okay. This is referred to the xy coordinate system because within it you have the various components epsilon xx, epsilon xy, epsilon yy, epsilon zz, all those things in terms of the partial derivatives of the displacement components. But you are interested along two directions given by this n1 and n2. Okay. Now, corresponding to those two directions, you are going to have a certain shear strain. That shear strain is given by this. Okay. That shear strain is given by this. Fine. So, pictorially, what does it look like? So, at this point, you have x, you have y. Refer to these coordinate systems, refer to this coordinate system, you have the epsilon. Just that, nothing else. But now, you are interested in finding out the shear strain corresponding to two line segments which are mutually perpendicular to each other. These need not be x and y. This x and y is our choice as a mathematician or an engineer. Okay, but the problem may demand that we are interested in the shear strain corresponding to two other line segments like this. And these may be x dash and y dash. You see where I am going with this? So x dash and y dash. The n1 hat, this thing, will be along the x dash and the n2 hat will be along the y dash. Initially the angle between them is 90 degree as it was supposed to be because this needs to be 0. Okay, the n1 dot n2 is 0. And you have all the information with the epsilon regarding about the epsilon. So given n1 and n2, you can find out the shear strain which will be present between these two line segments, between these two directions. Okay. Now, if you appreciate this, you have appreciated a lot actually. Okay. So going back to the earlier thing which we had obtained, remember epsilon is equal to we had obtained this earlier and I had left it with just the analogy between this and what we had obtained in the stress chapter. But in terms of this newfound realization, can you tell me what is the pictorial representation like this? From this diagram only you can tell me. What is it telling us with respect to this diagram? Exactly, exactly. So here you see that maybe, let me write it explicitly here, that along the x dash we have the n1 and along the y dash I have the n2. But here I have only one unit vector direction. Which is that? It can be anything. Let us call this x dash. So if you have this x dash, then along that you have a unit vector, and that's if someone asks you that given the state of strain at a point with respect to the coordinate axis x and y, you have this information, all the 6 elements, the 6 independent elements, you have the information. Using that, you just need to be asked that what along a certain direction, maybe n1, maybe n2, maybe n3, whatever is given to you, just substitute it here. What you will get is the engineering normal strain or the normal engineering strain along that direction. That's it. Yes.
Like considering theta equal to 90, if we find the general formula,
So the general formula is this.
this is only specific cases.
For 90 degrees. The reason for choosing it 90 degrees is that for shear strain, the fundamental definition tells us that. The shear strain, what is the shear strain? The shear strain is the change in the angle between two elemental line segments which are initially at 90 degrees to each other. We don't keep on saying this because usually what we do, and none of the textbooks tell us this, is that we say that gamma xy, gamma yz. But what is gamma xy? It is the shear strain corresponding to two elemental line segments which are oriented respectively along x and y. What is implicit and not explicitly stated is that the angle between those two line segments is always 90 degree. Again, you have things like gamma yz, you have things like gamma zx, all of those things have 90 degrees in between them. That is never stated explicitly, but now we are stating it, that if this is so,
Generally, if we think of shear, what it be theta minus theta dash.
no. Because we will not define shear strain like that. However, as a mathematically minded person, you may choose to call that something. You can call it Donald Duck strain.
So,
Donald Duck strain. Let's call it Donald Duck strain. Okay.
any strain that is acting on lines.
What is your name? What is your name? What? Sarvesh. Okay. Sarvesh strain. No problem. Okay. If you don't like Sarvesh, maybe you are enemies with Sarvesh, you give your own name. Cut his name and you give your own name. Okay. All right. But the official definition of shear strain has to do with two line segments which must initially be at 90 degrees to each other. Okay. See, this is the problem, right? So if we all keep on defining our own versions of the strains, then we'll not be able to talk with each other. But once we fix it, that it is 90 degrees to begin with, then we are okay. Okay. All right. As it is, so many wars are happening. Engineers should not go to war against each other. Okay. So see, in terms of the fundamental things, this chapter is over. Okay, but we are going to simplify the things and make it directly useful and in a form which will be familiar with respect to the stress chapter. Okay, so that when you're solving problems, every time you don't have to start from all these fundamental basics, direct formulas you will have at your disposal. Okay, so let's do that very quickly. So what we'll do is, in the stress chapter, we had considered the physical condition of plane stress, and that allowed us to have a justification for considering the two-dimensional version of the general three-dimensional things we were doing. In a similar spirit, what we'll do is, we'll consider something called plane strain. Okay, so plane strain has a lot of, it's a little bit more difficult concept compared to plane stress, but in simple terms, at the second year level, I'll tell you something which will help you to remember it always. Plane strain. So in plane strain, what we'll have is, you'll have a beam-like situation, and just listen to me, okay? It will be anyway recorded. It is getting recorded, right? Huh? Please check. I'm always afraid. So in this situation, what will happen is that you are not going to have any variation along this direction, along the longitudinal direction. Okay, there will also be no load in this direction. So let's say that this direction is the z. Okay, and let's say that this is x and this is y. This is right-handed coordinate system, right? Okay, all right. So x, y, z. Um, okay, so along the z, there will be no variation. There will be no load along the z direction. There will be other conditions also which you don't need to worry about. The ultimate mathematical implication of this situation is that you are going to have epsilon zz equal to epsilon zx equal to epsilon zy or yz equal to 0. That's it. Okay, that's it. Now, if this is true, then the strain matrix, which had things like this, this goes away, this goes away, this goes away, this goes away, this goes away. So ultimately, what you have is just a simpler version of it. Fine. Now, one small point of confusion that you may have is that we have considerably simplified everything, but we are still sticking to this capital X and capital Y, all these things, right? So one small thing that you accommodate is that sometimes in the question paper or in certain textbooks, you will see that they do not distinguish between the small x and the capital X. It does not mean that small x and the capital X is the same. If that is so, then there is no deformation. Okay, it is not like that, but this is just convention to keep on writing it like this. Okay, so if you ever go on to study continuum mechanics, things involving finite deformation theory, then you will see that how you are defining the strain with respect to what will make a world of difference. Okay, but at least now you don't have to worry too much about it. So we proceed with these things and we remind ourselves once more that epsilon xx is very much this del u del x, epsilon yy is del b del y, epsilon xy is equal to half of del u del y. Okay. Now, given that we have already obtained some useful formulas, can we not perhaps use them like strain transformation formulas? So earlier, when we had in the stress chapter, when we had those x, y, and we wanted to transform with respect to the x dash, y dash, we called those the stress transformation formulas, right? Okay. So in a similar vein, we are going to obtain the strain transformation formulas. So let's do that. So I'm keeping this just as a point of reference. Can you close this, please? Okay. So or maybe we'll just call it small x. Epsilon x dash x dash. Okay. What will be epsilon x dash x dash? Look at that. That is the epsilon x dash x dash. Okay. This formula itself. So this one corresponds to this picture. Okay. So x dash is oriented at an angle theta to x, which means the unit vector along the x dash will be what? This thing. Okay. Which means what we'll have is right. Please do not painstakingly expand it. Flip back to your notes and tell me the answer. E epsilon xx cos square theta plus epsilon yy sin square theta plus epsilon xy sin theta cos theta. There is no twice here. Sin 2 theta. Okay, so let's write like this. Sorry? Epsilon xy and gamma. Very good. There is a factor of 2 in between them. Yes. So this thing, okay, this thing is called the shear strain. Okay. And let's say that this is our epsilon x dash y dash. Right. This is referred to as the, so everyone please listen very carefully. This is a very, very important point. Gamma x dash y dash or gamma y dash z dash or whatever. Okay. This is referred to as the shear strain. And when we write epsilon x dash y dash, we can write epsilon x dash y dash, that is your question. So this also is referred to as the shear strain. Okay, don't ask me why. It is not called the half of shear strain or something. It is also called the shear strain. So depending on the context, you have to figure out who is meaning what. Okay, but this thing, the actual thing which you have to understand is that the gamma it is twice of this thing. Okay, which means that this version, the epsilon x dash y dash, this version of the shear strain, this is the average of the change in the angle between two line segments. Okay, so remember we had this picture. This is gamma. So whatever this angle and this angle, let's call this alpha and this beta. So this gamma is equal to alpha plus beta, right? And let's say this is the x dash y dash. So the epsilon x dash y dash will be equal to half of alpha plus beta. Okay, so it is as if we are taking the average of those change in angles. Okay, all right. Now since we have already written this, can we quickly write down the expression for the epsilon x dash y dash for this picture only? So we have this x dash. Let's write this as y dash. You tell me the expression of epsilon x dash y dash, Charit.
Sigma
Sigma
epsilon yy minus
epsilon yy minus epsilon xx. Alright, tell me in terms of these things now. Or you want to, okay, tell me. Into?
sine by 2 sine theta
Okay,
epsilon xy
plus epsilon xy cos 2 theta. Okay, so that's it. Okay, these are the strain transformation formulas. Now, since we are already on our way to doing things by analogy with the stress chapter, why not find out the expression of the principal strains also like this and finish off? Okay, so tell me. There is a proper proof of the principal strain thing which I have very nicely put in the tutorial sheet. Okay, that is especially meant for people who are having some motivation of going for higher studies. Okay, if you do not have, you don't have to do all those things. By analogy with principal stress. Okay, tell me epsilon P1, P2. Tell me the expression. Without any shame and embarrassment, you tell me. Oh, you have not written. Achha, anyone, somebody else, please tell me. Epsilon xx plus epsilon yy by 2, that thing, yes. Epsilon xx plus epsilon yy by 2 plus minus plus that's it. These are the principal strains. Okay. However, when we were talking about the principal stresses, we talked with reference to a certain plane, that we had a three-dimensional body like this, okay, and all within this body at different points we'll have different states of stress. Now if we cut this body at a certain on a plane, then it may so turn out that on that plane the shear stresses are zero, and on such a plane whatever the normal stress is, we will call that as the principal stress. This is the general notion. But in the case of strain, we do not have such a thing. Okay, it is certainly true that where you have this epsilon P1 and epsilon P2, the principal strains, the shear strains are zero. But you do not have associated with it a concept of a plane like you have in the concept, like you have in the case of stress. Okay, because stress intrinsically is associated with the definition of traction. Traction can be defined on a certain plane. Okay, for this you only need directions. Okay, you don't need planes.
And then more circle.
Morse circle can also be drawn, because see, Morse circle is motivated only by the geometrical and the like the variables form. Here also you will have that's exactly the same form. Okay, but let me tell you something. Professionally, I have never used Morse circle for strains. For stresses, maybe a little bit I have used, uh, but for strain I have never had to use Morse circle. Okay, but it is good to know. Okay, it's good to know. So that's it. That I mean, you have the this is the chapter. Okay, so in a similar form, you can find out the angles and everything. Now there is one topic left. We have sufficient time. So there is one topic left, which is a very, very practical experimental kind of topic. Okay, but it gives you a nice understanding of everything that you have done till now. Please note that it is not such a trivial exercise to determine the strain in a body when it is subjected to different kinds of loading. Okay, you take any body, whether it is a beam or some kind of a shaft and whatever, a three-dimensional body, and you load it. It is not so easy to find out experimentally the strains. So you have to come up with various ingenious ways of finding out the strains. So one method, there are various sophisticated methods. Some of them you will learn in your sixth semester. Okay, when you do one course on, there's a lab. Okay, so you'll do that. Now, one basic method has to do with something called a strain gauge. Have you heard of strain gauges? Those of you who are interested in the DIY electronics kind of things, maybe you have heard of it. So strain gauges. So maybe in your plus two also you had something like this. Mechatronics lab you had something. Okay, good. So anyway, I am not going to presuppose any knowledge on your part, but it is basically an experimental device, I would say, by which you can measure the strain in an indirect fashion. So what happens there is that uh, uh, we make the connection with resistors. Okay, a strain gauge is basically like a resistor. Okay, now you can have change in the dimension of the resistor, because you know the formula from class 11 and 12, that resistor is equal to the rho into L divided by A. Okay, so when you attach a strain gauge to a body, and please note that you can attach a strain gauge only on the surface of a body. So when the body deforms, the resistance will change. And if the resistance changes and it is part of a Wheatstone bridge, then you can actually measure the voltage that is indicated on the dial. Okay, so in a very, very indirect fashion, we can find out the strains in the body, and from that we can find out the stresses in the body. Now, whatever I have said, it may sound like mumbo jumbo to you, but I just wanted to give you a very brief introduction. So later on, when you do the lab, we will spend like almost 1.5 hours doing this only. Okay, we may also ask you to do the circuit yourself. So anyway, coming back to this thing, where is the strain gauge and where is this all the strain transformation formulas? So uh, think of it like this. So suppose you have a body, a cantilever beam, let's say. Suppose you have a cantilever beam like this, and you wish to find out the strain which is present on the top here, okay, at this end. Now, literally, a strain gauge is just like a little strip, very delicate little strip, okay, even smaller than band-aid, much smaller than a band-aid actually. So the actual like operating dimension of a strain gauge, if you look at it, it is almost like the little SIM cards that you have, okay, but much thinner than that. Okay, so you take it and you literally stick it onto this, okay, using some kind of a special adhesive. Okay, so you stick onto it, and then when you load it, this entire thing is going to deform. That part is going to undergo some kind of strain because deformation is taking place. We have already seen the route from deformation to strain. So when this thing deforms and this thing elongates, the strain gauge will elongate, the resistance will change, and if that is connected to a circuit, you'll pick up the voltage, and that is calibrated to the change in the to the strain, and you can read it out. But the thing that I want to say here is that if you just zoom into that part, okay, so you have something like this, that this is the surface of the body, and on this you have the strain gauge which is stuck like this. Let me draw a bigger diagram. Let me zoom into it very nicely. So I have this thing, and I have the strain gauge which is stuck onto it like this. Okay, the real dimension of a strain gauge is like this. It is much smaller than this diagram. Okay, so it is stuck like this. Now what the strain gauge will tell us, every strain gauge has a certain axis. Okay, so axis means this is the axis of the strain gauge. This is the axis of the strain gauge. Okay, like this. So this axis is the direction along which we'll be able to find out the strain. What does that mean? It means that arbitrarily you may have this axis. Okay, you may have this axis, these two axes, but when you are sticking it and you are reading out the value, you are getting the strain which is in this direction. It has no reference to this or this. Okay, it has no reference to this or this. You are just getting directly the value along this. That's it. Story finished. Okay, so think of it something like this. When you have a measuring tape, okay, a ruler, what do? Suppose imagine that this is a ruler, and you place the ruler like this. Okay, so maybe I should show on the board. You place the ruler like this. When you place the ruler like this, then what is it measuring? It is measuring the length from here to here, or maybe whatever intermediate point you are interested. It is certainly not going to measure this length, which is horizontally below it, or it is not going to measure the length which is vertically here. Okay, so the device that you have in your hand, you'll be able to find out the strain or that what you are measuring along that device direction. This is the thing. So this is good. It gives us a direct measure of the strain along a certain direction. But the problem is that if you are actually interested in finding out the complete state of strain that exists at a certain point, then using one strain gauge, you are not going to get the entire information. You are only going to get one information along a certain direction only. That's it. Story finished. So what are you going to do? Sorry? Two strain gauges. Okay, two strain gauges. So actually what is done is some combinations of strain gauges are used. Okay, so usually 3 strain gauges are used, and they are arranged in various types of combinations. Okay, some formal names are there: delta combination, star combination, all these things. Okay, basically what they are doing is arranging the strain gauges at different angles. The names are just fancy names. Okay, so you have strain gauges which are oriented like this. This is one particular orientation. And you do not have to take the trouble. Okay, you do not have to take the trouble that you will buy 3 strain gauges and then you will go about sticking all of these things in this particular combination and then worry whether it is 45 degrees or 46 degrees. Okay, you don't have to worry. You can actually buy strain gauge which comes in a nice combination. Okay, this is 0, 45, 90. Why do we need 3 strain gauges? Think, you know the answer. At a certain point on a plane, how many unknowns are there? Epsilon xx, epsilon yy, and epsilon xy. All three things are unknown. When you say that you know the state of strain at a certain point, you have to say that I know the values of each of epsilon xx, epsilon yy, and epsilon xy. Only then you can claim that you know the state of strain at that point. So since three unknowns are there, you need three strain gauges to find out the values. Now this particular combination, not necessarily 45 degrees, it could be 60 degrees also. You can have strain gauges which are oriented like this. Okay, very bad drawing by the way, but they are at 60 degrees. Okay, so you can have various combinations, but you need to have three things. Only then you will be able to find out the complete state of strain. So what is going on? Mathematically, what is going on? Suddenly we have not shifted gears and moved on to a lab course. Okay, so what we are going to do is just to write the expression of each of these strain gauges, the normal strains along those directions in terms of the epsilon xx, epsilon yy, and epsilon xy. Okay, and by reverse engineering we'll be able to find out the things. So it is like this. So these combinations of strain gauges, these are referred to as strain rosette. Okay. Combination of strain gauges. So let's say that, just as a simple example, just to concretize our ideas, we have one strain gauge like this, we have another strain gauge like this, and we have another strain gauge like this. I will not claim that this is 45 degrees. I will just say that this is some theta b and this is some theta c. Sorry. This is theta c. So this is strain gauge A, this is strain gauge B, this is strain gauge C. We have these three strain gauges A, B, and C. Okay. So if we have the XY axis like this, suppose this is the XY axis, then you tell me in this particular case theta A is what? You imagine that this is our x dash. This thing is along the x dash, but the x dash happens to be along the x. Okay, so earlier I had said this, right? You have x like this and you have y like this. So in general, if you have a strain gauge which is like this, a theta, I can say that this axis is like this x dash. Okay, so for each of these strain gauges you will have an x dash oriented along its axis. So this thing is what? For the theta A, 0. This is 0 degrees. Theta B will be something which will be known, and theta C is what? 90 degrees. Okay, if you have a strain gauge which is like this, and then maybe another strain gauge which is like this, and another strain gauge which is like this. Let's say this is A, this is B, this is C. Okay, and let's say this is an equilateral triangle. Then what is theta A? 0. Theta B is what? 60 degrees. And what is theta C? 120 degrees. That's it. You have got it. Okay, so all that we have to do now is very quickly we can write down the general expressions for the three strains. In general, okay, in general for epsilon A, it will be we are going to use this formula. Okay, the epsilon x dash formula. Epsilon b will be, tell me what is this? Cos square theta b. Don't be afraid. Cos square theta b. So over here, what are the things that you do know? Do you know the value of epsilon A? Yes, because you can directly read it out. Okay. So when you are using the strain rosette, this epsilon A will be directly available, epsilon B will be directly available, epsilon C will be directly available. What else do you know on the right hand side? Theta A and theta B and theta C. So all these things you know. And what do you not know? Okay, so the unknowns are epsilon xx, epsilon yy, and epsilon xy. Three equations, three unknowns. You can find it out. Okay, basically you will have three linear simultaneous equations. You can find it out. That's it. This is actually strain rosette. Okay. All right. Thank you.